Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, welcome to this presentation of our final semester project. And here is with me, Alicia Naura Salsabila as your presenter today. And in this video, I'll be walking you through the process and the key aspect of our project focusing on the design, electrical system, and the program that powers it. The project was developed as a part of our final assignment, combining both theoretical understanding and hands-on application. And throughout the semester, we worked on building a solution that's not only functional, but also designed to meet specific needs that and its constraint. In this video, we will explain you the design choices that we made, the electrical components and the wiring involvement, and the logic behind the program that we provided to the control system. I hope this explanation helped you to understand the overall concept and technical details behind our project. So, let's get started. First of all, let me introduce you our team member with me here, Alicia Naura Salsamita, Domenico Adiputra Simanjuntak, and Sinta Duyani. We begin the project by carefully analyzing the system requirement specification that defined by the PRC 2020 for completion. The completion rules required our robot to meet several constraints, which directly influence our design and decision. First, start with form and factor with mass. The robot has to start within 150 millimeters for the weight, length, and height. For its dimension that only could explain up to 200 millimeters during the operation, and its total weight must not exceed 3 kilograms. This constraint forced us to adopt a compact, efficient mechanical design. And the second one, we have a control and communication where, although no remote control was allowed during the run, Bluetooth modules such as HC05 or YP could be used for the logic and initial setup for the control by manually with UI interface. And we have object manipulation capability where the robots was required to pick up a small objects such as marbles and miniatures using a gripper. This required a reliable and effector, which led us to choose a custom mechanical arm over a forklift alternatives. And lastly, we have the autonomy and control, where the robot must be fully autonomously, meaning there is no remote control was permitted during the competition. And to fulfill this, we installed a combination of line following and proximity sensors for environmental awareness and text navigation. Well, these requirements serve as the blueprint throughout our mechanical design, component selection, and software logic development. Despite having a clear guideline, we encountered five major technical challenges during the development as documented in our final project report. First, we have a limited component availability. There are many ideal components such as highly torque servos or compactly powered batteries were either unavailable or beyond the budget. And the microcontrollers such as Arduino and Mega that included the Bluetooth or the Wi-Fi module, and that was not available too. This required us to find alternative components such as replacing standard grippers with gear link servo system. And second, we have a compact and efficient integration where the given small decision limit arranges all the electronics, motor driver, Arduino, Bluetooth module, battery, sensor, and gripper within a confined cases require a creative spatial plan. We address this by shifting from an ESP8266 to a smaller Arduino Nano and restricting our wiring path vertically. And we have the software errors and limitation. Our initial firmware had issues with unstable sensor readings and servo jitter, particularly in the gripper. These were solved through the sensor calibration, analog signal smoothing, and delay tuning with the main controller. And we have a component fragility, where the MG90S servos and N20 Motors, therefore, were prone to overheating and physical damage. To mitigate this, we reduced overriding loads using gear reduction and distributed force more evenly across the yard. And lastly, we have power and energy management. Because we had only used one power source, any imbalance in the current draw would affect all the system. We solved this by isolating powers to motors and logic circuits using buck converters and limiting servo data cycles. Overall, this problem remained a continuous testing, debugging, and refinement, also emphasizing the importance of our iterative and adaptive process.
Sketch design 1 and 2 on the slides. You see our first sketch. Sketch 1 prioritized a central chassis gripper. Sketch 2 explore an off-center arm for better weight distribution. We use morphological analysis, listing function like grip, lift, rotate against geometric layout. To generate this concept, then we vote anonymously to surface the most promising ideas. Next, previous semester design, we revisit legacy design from last semester, evaluating what worked well. We plotted performance against complexity in a quick trade space matrix, identifying that a conventional arm offers more adaptability than a forklift mechanism under our size constraints. Next, preliminary design. Having selected the conventional arm, we move to concept refinement. We fix our key components like Arduino Nano, L208N driver, BFD1000 sensor, MG90S servo, GA12 and 20 motor, and produce the preliminary CAD layout. This is an example of a stage development model. We complete We complete concept review before entering preliminary design, ensuring each stage deliverables draft the next. Next slide. Critical design. In the critical design phase, we perform detailed technical review, safety, cost, supply chain risk, ergonomic. We use a spiral development mindset. We iterated on component selection, based on risks and tested small increment of the system in each loop. This ensures that no single decision jeopardizes the entire schedule. Next slide. Draft design and prototyping. The draft design slide shows our first physical prototype. We conducted rapid prototype tests, wiring harness check, static fit test, basic motor runs. This is where we applied agile sprints, short 1 week cycles to implement and test specific subsystem, like e.g. one sprint for motor control, one for sensor integration. Feedback from each sprint was immediately incorporated. Next, final design. In our final design, all modules, mechanic, electronic, firmware, and UI were integrated. We held a final design review against our original requirements like size, weight, autonomy, and object handling. Any deviation were ironed out in a last-minute agile iteration with 48 hours turnaround on minor firmware tweaks or mounting adjustment.
In this section, I will explain the development of the electrical wiring diagram of our line follower robot, which is designed to operate in both automatic mode and manual mode with control via Bluetooth module, where the primary goal of this wiring design is to enable the robot to switch between two control modes. First is automatic mode using infrared sensor to follow a line on the ground, manual mode using either a Wi-Fi or based controller or a Bluetooth module to drive the robot remotely. This dual mode control required careful planning in terms of microcontroller selection and pin usage. Initially, we considered to using the ESP8266 module because it's built in with Wi-Fi capability. However, the ESP itself has a very limited number of GPIO pins, which made it difficult to connect all the requirement components. Our second option was the Arduino Uno Wi-Fi Atmega 828P, which has a large number of GPIO pins and is ideal for complex robotic projects. However, due to the hardware unavailability and physical size constraint, the Mega could not be used in our robot cases. This led us to search for more a compact yet a capable alternative. Eventually, we selected the Arduino Nano as our final microcontroller. The Nano offers a balanced number of the pins and a compact form factor, which allowed us to connect all the sensors line to the line following function. The interface with the L298 and motor driver module and either the HC05 root module through a software serial. Utilize both manual and automatic controls via logic switches or software commands. Electrical wiring diagram plan with Arduino Nano as our final electrical wiring diagram plan. In this part, I will explain the wiring diagram and the reason behind the pin selection used in our final project. First, the BFD 1000 line sensors with 5 channels from S1 to S5 that is connected to the analog pins of Arduino Nano A0 to A4. These analog pins are chosen because the sensor gives analog output, which needs to be read using analog inputs to detect the line properly. So, next we use two MGs 19S servo motors for both robot's arm and gripper. These are connected to the digital pins of D9 and D10 because these pins support PWM signals, which are needed to control the angle of the servos accurately. Then, for controlling the 2 and 20 DC motors, we use the L298 and motor driver that connection 2 and 1 to day 5 and 2 to day 6 and in 1 to D3, in 2 to D2, in 3 to D7, in 4 to D8. Pins D5 and D6 are PWM capable so we can control the speed of each motor. The other pins are used for setting the motor direction. And for the wireless control, we use the HC05 Bluetooth module. The TX pin of the module is connected to A5 and the RX pin is connected to D4. We choose these pins because if we are using the software serial, the default serial pins in D0 and D1, it will cause a complex communication of Arduino Nano USB communication. So, using A4 and D4, using A5 and D4 helps avoid crashes and let the robot be controlled both through Bluetooth and USB without issues. Lastly, the whole system is powered by the two NCR18650 batteries, each with 3.7 volts and 6,000 mAh capability. These batteries are chosen because they can provide enough power for the motors, servo sensors, and the Arduino itself to run smoothly. This wiring configuration was made by carefully considering the function of each pin and the stability of the communication and power in the system.
Hello everyone, my name is Sinto Diani as programmer team Line Follower A3. Today I will to presentation about algorithm. As you can see here, there are two flowchart, one for manual control and the other for autonomously control. The first manual control flowchart. This flowchart illustrates the logic flow of the program for the robot manual control mode. The process starts from start and continues to the initialization of sensor and motors. After that, it processes to read manual read manual input where the system read the input values from the user. If yes, based on the manual input, the robot can move forward, move backward, turn left, turn right, and stop motor. Then, the robot will execute the command according to the input and the program ends. Next, the second, autonomously control. The process starts from start and continues to the initialization of sensor and motors. After that, it's processed to read automatic input, where the system reads input values based on the line sensor readings. Based on this input, the robot can identify intersection and checkpoints. If all five sensors detect a line, or all sensors are active, the robot will execute commands programmed by the developer such as moving forward, backward, turn right, turn left, or stop motor, depending on the intersection present on the provided track. The process the end. Okay, and finish. Thank you.
That concludes our presentation for the final semester project. To summarize, we've explained the design process, the electrical configuration, and the programming logic behind our system. Each part was carefully planned and developed to ensure the functionality and performance of the final result. This project has allowed us to apply what we've learned throughout the semester into a real working solution and has also helped us better to understand the challenges of integrating hardware and software in a practical setting. I hope this presentation has been clear and informative. If there are any questions or feedback, I'd be happy to hear them. Thank you for watching, and I hope this explanation was helpful and insightful. Wassalamualaikum warahmatullahi wabarakatuh.